back in Calculus 1, we had functions that were compositions, and we wrote y as a function of u, where u was a function of x. Now, to find the derivative of a composition, we had to use the chain rule. And we saw that the derivative of y with respect to x was the derivative of f with respect to u times the derivative of u with respect to x. Or another way to write that was f prime of u times u prime of x. Now, we will now have two variables for a function. So we have a function such as z equal f of xy, but we want to consider when both x and y are functions of another variable. So t will be our single independent variable. We'll have that z depends on x and y, but x is a function of t, and y is a function of t. So what we need to do is figure out how do we find the derivative of that function z, where you have x and y both depending on another independent variable t. Now the x and the y here are called intermediate variables. The z is your dependent variable, and your t is your single independent variable. Okay, now we're going to use a tree diagram to help us to visualize what this chain rule is going to look like. We have that z depends on both x and y, and you get that by looking at the function z being defined in terms of x and y. So we have z dependent on x and dependent on y. But then we see that x is a function of t, so x depends on t, and we see that y depends on t. So the change in z with respect to x, since x is one of two variables, we would need to take the partial derivative of z with respect to x. But x has a single independent variable t, so when we take the derivative of x with respect to t, we'll just have the regular derivative. Likewise, z depends on both x and y, so if we're going to differentiate z with respect to y, we'll use a partial derivative. And since y has the single independent variable t, the derivative of y with respect to t will be just the regular derivative, dy dt. So now the contribution of the change in z with respect to t has two ways to affect it. One would be the change in z due to that variable y. So look at the different paths in this tree diagram that end with the t. We have a contribution of dz dt from this path, and the amount of that contribution is the change in z with respect to x times the change in x with respect to t. Likewise, there's a contribution to dz dt coming through this other path. Find the change in z with respect to y, which would be a partial derivative, times the change in y with respect to t. So we've looked at how x and y are both affected by the change in t. And that sum of those two rates of change will give us the change in z with respect to t. So the theorem 13.7, if z is a differentiable function of x and y on its domain, x and y are both differentiable functions of t, then dz dt will be the partial of z with respect to x times dx dt, plus the partial of z with respect to y times dy dt. So that's the chain rule when you have that z is a function of x and y, and x is a function of t, and y is a function of t. So that gives us the change in z with respect to that independent variable t. So let's see what that looks like. I want to find dz dt when we're given a function here, z, in terms of x and y. So our z is actually a function of x and y, but since x is a function of t and y is a function of t, z is also a function of t. That's the independent variable. So to find dz dt, let's use our tree diagram. We have that z is a function of x and y, and you can get that by just seeing the variables in the equation. But x is a function of t, which you see from this, and y is a function of t. So labeling each of the paths, we would have a partial of z with respect to x here, because there's two independent variables under the z, and the partial of z with respect to y. They're partial derivatives because there's two variables at that level. Now, x is only a function of t, so that's dx dt. We don't need partials. And this one is dy dt. So coming down the path, this first path, take the product of those two derivatives. So dx dt is the partial of z with respect to t, respect to x, times the derivative of x with respect to t. And now the second path, the partial of z with respect to y times dy dt. Now, find each of these derivatives, the partial of z with respect to x. So look at the derivative of x, of z, in the equation that's in terms of x's and y's. So if we're finding the partial of z with respect to x, the y would be a constant. So this will be 2x. Now the derivative of x with respect to t. Find the equation for x in terms of t. The derivative of x with respect to t will be negative 2 sine of t. Partial of z with respect to y, negative 6y. And the derivative of y with respect to t would be 2 cosine t. So dz dt is negative 4x sine of t minus 12y cosine of t. Now, if I want to evaluate that, notice it has x's, y's, and t's in it. We could change that to a single variable t by changing the x to 2 cosine of t and the y to 2 sine of t. But if they just want us to evaluate it, then we could leave it that way and then just plug in t equal pi over 4. Now, if we're going to do that, though, we would still need to find out what x would be for the value of pi over 4 and y for the value of pi over 4. So to simplify and only have to plug in t for one variable, let me go ahead and change this over to all t's. I have minus 4x, but x is 2 cosine of t. Minus 12y, but y is 2 sine of t. So that's minus 8 sine t cosine t minus 24 sine t cosine t. So we have negative 32 sine t cosine t. Now you can go ahead and plug in pi over 4 for the t here. If you want to use your trig identities and recognize this sine t cosine t, and remember that 2 sine t cosine t would be the same thing as just sine of 2t. Then I could change this to negative 16 sine of 2t, just to make it a more simplified expression. But there are equivalents, so it's not necessary. So that's the dz dt in the most simplified form. The one above it should be just as good. Now evaluating it at pi over 4, we would have minus 16 sine of 2 times pi over 4, so that'll be pi over 2, which comes out to be a negative 16. Okay, so that's evaluated at pi over 4. Now another way you could have done this problem, if you were looking for dz dt, is you could have taken z and rewritten it all in terms of t to begin with, by changing all the x's to 2 cosine of t, all the y's to 2 sine of t, and getting this equation in terms of just the variable t. But we were trying to practice the chain rule, so we're not going to do that now. But you should get the same exact answer doing it either way. Okay, now let's look at what is this mean geometrically. We just found the partial derivative. Well, we found the derivative of z with respect to t. Look at what these two equations actually create. X equal 2 cosine t and y equal 2 sine of t. If you recall, this is parametric equations for a circle of radius 2. So looking at x and y down in the xy plane, we have a circle radius 2. So what was happening then, if we started, let's see, that actually would have a starting value when t was 0 would be at 2 comma 0. And so when t is equal to pi over 4, it would be at this point right here. Now, what you're doing is you're looking at the point on the surface, which is above this point in the plane. So if you go straight up from this point, here's the point on the surface that's defined by this z value. And as you're moving around that circle, you're tracing out a path on that surface. And so you can see that the path, this would be the path that the object is taking along the surface as the x and y values are moving around the circle in the xy plane. Okay, so the x and y locations of points depend on the t values, and we're looking at points on the surface. So now what you just found by finding that derivative at t equal pi over 4 is you found the slope of the tangent line to the curve at that point on the surface. So at this point here, which is directly above where the point would be on that circle at t equal pi over 4, we found that the slope of the tangent line was negative 16. So the change in z relative to the change in t is negative 16. So you can see a really steep, decrease in the z values at that point. So the slope of that tangent line, the change in z with respect to time or t is actually negative 16. So negatives indicating that it's decreasing, and 16 is telling that every change in 1 for t results in a change of 16 for the z values.